Hi guys, hope you're having a wonderful day. We are continuing thermochemistry. We've learned so many different ways to calculate delta H, or the heat transfer in a reaction, and this is our very last way, which is called Hess's law. And we typically use Hess's law for reactions that we can't really carry out in the lab, like maybe they're dangerous, maybe they require a lot of time, maybe they require extreme conditions or something like that. And Hess's law relies on the idea that heat is a state function, meaning that it is independent of the pathway. It does not depend on the pathway. What matters is the potential energy of the reactants, potential energy of the products, and that's it. So it's similar to displacement. For example, so if I want to walk to the door in the room here, I could walk straight to the door, or I could walk around the room and then get to the door. My displacement would be the same, because displacement is a state function. What matters is my initial and my final position. The pathway does not matter. Distance, however, is not a state function. My distance in both ways would be different, because it depends on the pathway. So heat is like displacement. They're both independent of the pathway. It does not matter whether you carry out the reaction in 1 step or 100 steps. Delta H would be the same if your reactants and your products are remaining the same. So in a Hess's law problem, you'll know it's a Hess's law problem. If you are asked to calculate delta H for a certain reaction, and then you're given a series of other reactions, 2 or more, with their delta H's. So the goal is you need to add these reactions up, manipulate them sometimes, and then add them up. And when you add them up, you get the overall equation. And so that means if you add up their delta H's, you'll get the delta H for the overall equation. So the way that you would do this is you would look at the equation you're interested in, which is this one right here. And you'd go through each of the substances. So let's start with carbon. So you check which equation has that carbon. I'm going to call these 1 and 2. So equation 1 has carbon. You check 2 things. You check that it's on the correct side and the correct coefficient. Correct side meaning here it's a reactant, and so here it's also a reactant, so that checks. And then the coefficient, this means just 1 carbon. This is 1 carbon, so that checks. So no need to manipulate that equation because it checks in both the side and the coefficient, so all you have to do is just rewrite this. And it's delta H. Okay, next we see O2. Where do you find O2 in which of these? Well, it's in both. So here's a helpful Hess's law tip. If you find a substance in more than one of the given reactions, skip it. Don't worry about it. Do the other substances. It should work itself out. So since oxygen is in both, we're going to skip it. We're going to go to the next substance. Next substance is CO2. Where do you find CO2? Well, we find it in equation 2. And check, is it the correct side? Yes, it's a product here and it's a product here. Is the correct coefficient? 1 and 1, so that's good. So just rewrite that equation, no need to manipulate it. CO plus half O2 yields CO2. Delta H is negative 283.0 kilojoules. You know that you are done when one of 2 things happen. Either you are going to go through each of the different substances in your equation, which we just did. That means you're done. Or you would have used each of your steps, each of your equations that you have delta H's for. So we've used both of them. So that both of these things are telling us we are done. So now we check. What we're checking is that when you add these 2 equations together, you get the overall equation that we wanted. So to add them together, what that means is all the reactants from all the equations are on one side, arrow, and then all the products from all the reactions. If you see something on the reactant side and on the product side that's the same, you can cancel those out, just like in math. So here I see carbon monoxide on the reactant side and carbon monoxide on the product side, so I can cancel those out. Nothing else cancels, so what you were left with is carbon plus half O2 and half O2, that's a full O2, and then yields CO2. Does this overall equation match the equation that we wanted? Yes, it does. That means we did it correctly. So now all we have to do is add up our delta H's just like we added up our equations. So negative 393.5 kilojoules. That is the answer. That is the delta H for the formation of the carbon dioxide here. Now, this was our first example, and so we didn't really have to manipulate any of the equations, we just kind of rewrote them. Let's do one where, it's a little bit more fun, where we actually have to manipulate some of the equations. So here's the equation we're trying to find. It's delta H, the formation of CH4. So C plus 2H2 yields CH4. And here are 3 steps that we're given with their delta H's. So we're going to start with our first substance here, which is carbon. So I see that in equation 1. I check 2 things. It's the correct side, yes. Reactants and reactants, is it the correct coefficient? Yes. 1 and 1. So no need to manipulate equation 1, you just rewrite it. And rewrite its delta H as well. Okay, next is 2H2. I see the 2H2 in equation number 2. Let's check, is it the correct side? Yes. This is a reactant here, it's a reactant here. Is it the correct coefficient? No, it's not. We wanted to say 2H2, but here it says just 1H2. So we need to manipulate this equation so that this looks the same as what we wanted here. So what do? Well, we multiply this equation by 2 so that it says 2H2. So we're going to multiply the whole equation by 2. Whatever you do to the equation, you also do to the delta H. So we're going to rewrite this multiplied by 2. So 2H2 plus 2 times half is 1O2 yields 2H2O. My delta H would be also multiplied by 2, so that's negative 571.8 kilojoules. Okay, we did the 2H2. Now we're going to go to CH4. Where do you see CH4? You see it in the third equation, and you check the coefficient, 1 and 1, so that's good. You check the side, this is a product, this is a reactant, that's not good. So we need to manipulate equation 3 so that it looks like this. So what do if it's on the wrong side? We flip it. We flip the whole equation. Whatever you do to the equation, you do to the delta H. What does flipping the equation mean? That means that you reverse it. So you look at the reverse reaction. That means the reactants become products, the products become reactants. So we're going to rewrite equation 3 flipped. So my products are going to be my reactants now. So CO2 plus 2H2O yields CH4 plus 2O2. If we flip the equation, we have to flip the delta H. Flipping the delta H means you flip the sign. So if it's positive, you make it negative. If it's negative, you make it positive. So it's negative, so we're going to make it positive 890.4 kilojoules. If you've used each of your steps once, or if you've gone through the different substances in the equation you want, then you're done. So we know we're done. Now we just check. So to check, you add up your reactions, all the reactants on one side, then arrow all the products on the other side. Do you see anything that's common in the reactants and in the products that we can cancel out? I see 1 CO2 here and 1 CO2 here. I see 2H2O in the reactants, 2H2O in the products. I see 2 O2s in the reactants and 2 O2s in the product. And that's it. So what we're left with is carbon plus 2H2 yields CH4. Does this match the equation we wanted? Yes, it does. That means we did it correctly. So now all we have to do is add up our delta H's together. So negative 393.5 plus negative 571.8 plus 890.4 kilojoules. Altogether, that's negative 74.9 kilojoules. So the trick to these is manipulate your equations so the substances look like the equation you are looking for. Sometimes you do nothing to it, sometimes you flip it, sometimes you multiply, sometimes you divide, sometimes you flip and divide or flip and multiply, and so on. So it's kind of like a puzzle. I really, really enjoy doing these kind of like in my free time. Have a great day, guys.